All right, this is on page 14 of your notes. So we're talking about graphing sine and cosine functions. This video is just going to cover sine. So here we are. We want to graph this. Step one, using a graphing calculator to graph the function, and we did that. Zoom 7 trig, we did that. Let's talk about some vocabulary, because if you don't know the vocabulary, it's going to be hard to refer to the different parts of the graph. So the period is the length of one complete cycle. And with a sine wave, one complete cycle means this. So that's one complete cycle, because after that, it's going to keep going again and again and again and again and so forth. So for a sine wave, this is one complete cycle, kind of like a sideways S. When I think about it into 4 chunks, because it goes up, down, down, up. And we'll talk about that here in just a second. But that's one period. It goes through an entire period, the length of one complete cycle. The amplitude is how high does it go and how low does it go. And we say it's only half the distance because it has this middle line in between it. Let's go ahead and start graphing. So using your graphing calculator, you can look at your graphing calculator. You know there's a point at 0, 0. And at pi over 2, it is up here at 1. We need to set our y-axis. You probably don't know why I use that as 1. I'm going to say that this is 1, and this is 2, and this is -1, and this is -2. Why did I skip boxes? No reason really, except just if I didn't, it'd be really small and hard to see. So I'm going to skip boxes so I can make it easier for myself to see. All right, so it goes from 0, 0 to pi over 2, 1, comes back down to pi is 0. 3 pi over 2, I think a second ago I said 3 pi over 4. That was 3 pi over 2. At 3 pi over 2, it goes down to -1, and at 2 pi, it goes up to 0. Let's just check our table and make sure that's what we're supposed to have. 2 pi would be 6.28. Now, remember, we've talked about this before. When it has an e to the negative something, that's actually saying scientific notation, and that really means 0. To the -13th power means 13 zeros and then a 2. That really just means 0. Your calculator, for whatever reason, just cannot calculate that very well, and it comes up with this, but it's actually 0. So 2 pi is 0, and pi is 0, and 0 is 0. So 2 pi is 0, pi is 0, and 0 is 0. And then we would connect these and make a curve with them. That's one period. We can extend it into the negative values as well. It's going to follow the same pattern. So it's going to go down and then up again, and then down. And that is one period. So right here I have graphed 2 periods, one in the negative quadrants and one in the positive quadrants. All right, that's the length of one complete cycle is 1 period. I now have 2 periods. All right, the amplitude was half the distance between the max and the min values. So your maximum value is up here at +1. Your negative value is down here at -1. So halfway in between there, that just means it has a height of 1. That's the highest it goes, and the lowest it goes is 1. And so that is the amplitude. The frequency is the number of cycles in a given time. It's the reciprocal of the period. It's basically saying, okay, in 1 second, how many times is it going to go up and down? Okay, but it's just and so let's talk about for our graph, that's what I have over here in purple. In our graph, 1 period for it to go up, down, down, up, 1 complete cycle, it took 2 pi on our graph paper. In the span of 2 pi on our graph paper, it completed 1 cycle. So here, 1 period is 2 pi. The amplitude is 1 here. The frequency is 1 over that, and so that is 1 over 2 pi. And then phase shift is just another vocabulary word. It means horizontal translation. That's kind of like, we've been talking about HIVO all year long. Well, this is just another HIVO, but with trig, we just have a special name for it. We call it phase shift instead of horizontal translation. All right, let's look at this graph of sine and look at some important information. Where does it start? It starts at 0, 0. The sine function, the parent function for the sine, will always start at 0, 0. And from that point, it will go up. So you need to write that down. It's going to start at 0, 0 and go up. That's for the parent function. Now, of course, we can do things like reflect it and move it and whatever, but that's what it's going to do. Okay, let's talk about HIVO. I mentioned HIVO a second ago. Oh, before we do that, over here on the left, to graph this, for your x-axis scale, let's take the period and divide by 4. So in other words, once again, we're talking about, well, what about for a sine wave, or excuse me, a parent function? We're going to take 2 pi and divide by 4 in order to get our period. So here's my 2 pi. I divided that into 4 sections, and that's how I'm going to give my x-axis, okay? Translating the wave. The number in front is always the vertical stretch. We now call that the amplitude. So this one has a sine. It was just a sine of theta. That means there's a 1 in front, so it went up 1. If this was 2 sine, it would go up to 2. If it was 3 sine, it would go up to 3, etc. Then B is the horizontal stretch. That's going to change our period. I put the wrong symbol in there. Your period should always be 2 pi over B. That's how we find our period. This period on this parent function was 2 pi because we just had a 1. If you just have y equals sine of theta, then there's a 1 in front of that, right? And so this period was 2 pi because there was just a 1 in front of it. If this comes out to be y equals the sine of 2 theta, or 2x, then we would take this and divide by 2, and that would be our period. This is a little confusing because we haven't done an example yet. We will do an example, and hopefully that will help. The vertical translation is as it always is, the k. Whatever's added on to the end, that's our vertical translation. That means instead of starting here at 0, 0, it's going to start up here at 0, 1. Or maybe it'll start down here at 0, negative 1. But that's what the k is going to do. The number on the end is going to move it up and down, just like it always does for us. And the h is going to be the horizontal translation, the phase shift. So just like always, it's still in the right spot for our whole HIVO rules. That's the same thing. Plus means right and minus means left. So that's what that's going to do. It's going to move it left and right. That's called a phase shift. All right, well, let's do some of this then. Let's see what happens. Okay, let's graph the parent function first. So this might be, if you want to use 2 colors, this might be a good place to use 2 colors, or maybe a solid line or a dotted line or something. Okay, the first one is y equals sine of theta. We just did that one, so we know how it goes. It's going to touch at 0 and pi and 2 pi. I'm going to label my y-axis, and again, I'm going to skip just because that just gives me a little bit more space, so I'm able to fill some things in. And a sine function always starts at 0, 0, and then goes up, and then down, and then down, and then up. So that is one period. I can do the same thing over here. I'm basically just redrawing what I had up above. And so this is the function y equals the sine of x. And I put arrows on there because it'll continue this wave pattern both ways. Okay, what about y equals the negative sine of x? Well, we know that that negative, because of HIVO, that is going to be a reflection across the x-axis. That's called a vertical reflection. What does that mean? Well, for one, it means anything that's on the x-axis stays on the x-axis. If this is a reflection, then this axis is like our mirror. Anything on the mirror is going to stay there. But the things that are not on the mirror are going to get reflected over the other way. And so I'm going to take each of these and I'm going to reflect them in the x-axis. Okay, so now when I draw it, I'm still starting at 0, 0, but because it's a reflection, it's going to go down. It's going to start at 0, 0, and then go down, up, up, down. And once again, this is one period because I've come back and I've done all my parts of it and I've stopped. Basically, I did a whole cycle of it and ended up where I started from. Same thing this way. I'm going to go up, down, down, up, and I have my reflection. And so my blue line, for me it was blue, is y equals this negative sine of x. So that's just a basic example of a HIVO that if it is a negative, it gets reflected, and this is what it looks like. Let's turn the page and do another example. Okay, let's take a look here. We are not starting with our parent function this time. This time we have a 3 on one of them and a 1/2 on the other one. What is that number going to do? Well, that number in front is going to be a vertical stretch. Or in the case of the 1/2, it's going to be a vertical shrink. So we need to look at some things. And so these are two things where if you look at these before you start, it's going to help you set up your graph. Because the period is always the angle, the theta, and then we divide by the number in front of that. Well, there is no number in front of that. So in this case, our period is 2 pi over 1 for this one, which is just 2 pi. And for this one, it's also 2 pi over 1, which is just 2 pi. So that's easy because that means our period is going to be the same on both of them. And then to set up our graph, we're going to take that period and divide it by 4. And so 2 pi divided by 4 is pi over 2. That means we're going to count by pi over 2's. And once again, just like I had on the other side, I'm going to skip a space. So this is going to be pi over 2. This is going to be pi. This is going to be 1.5. And this is going to be 2 pi. And it's going to be the same going the other way in the negative direction. And so this is a negative 2 pi, and this is a negative pi, and I might get lazy and not label those other two. All right, the amplitude. Well, on our first graph, let's just call this graph A, and let's call this graph B. So our amplitude on graph A, the amplitude is going to be 3. That is, from the 0, it's going to go up 3. And from the graph B, our amplitude is only 1/2. Okay, so it's going to be a lot different. So because we only have 5 spaces here, I wish we had 6, but we only have 5, so we'll just count by ones. We're just going to go 1, 2, 3, 4, etc. And of course going the negative direction also. And really -3 is the only one I actually need. The other ones are not as important. So let's start off graphing 3 times the sine of theta. 3 times the sine of theta is going to start at 0, 0. Sine functions always start at 0, 0. And then it's going to go up 3 for the first quarter. The 2 pi over 4, when I reduce that, it comes out to pi over 2. So for every pi over 2, I'm going to go up 3 or down 3, and then another down 3, and then up 3. So this time I have the same period. It took the same space left to right, but it was taller. And then I'm going to do that same thing in the negative direction. And so it's going to go down, up, up, down. My drawing is not very good here. You really should not have pointy V's like this, even like this. Try to make them more rounded. When I'm drawing on this board, it's kind of hard for me, but it should really be a little bit more rounded like that, and even like that. Okay, try not to make them pointy. They really should not be pointy. Okay, so that is, we will call that graph A. Not very mathematical. I should have called those f of x and g of x, but here you go. The next one, though, it only goes up a 1/2. Its amplitude is only 1/2. So I'm going to have to pay attention to where's my 1/2 on here and where's my negative 1/2. Because once again, it is a sine function. Sine functions start at 0, 0, but this one is only going to go up 1/2 for every pi over 2. And then down 1/2, and then down 1/2. Oh, I went too far, and then up 1/2. Up, went too far again. And I can do the same thing in the negative direction, going down 1/2, up 1/2, up 1/2, down 1/2. And so now when I connect those, I'm going to get this really much flatter wave. All right, once again, it's difficult on this board for me to draw very well, but hopefully you can see on your own paper, but hopefully it's better than this, that it's going to just be much flatter. It still hits, it has the same x-intercepts, and it has the same period. It's just that the first one is taller and the second one is shorter. And so again, this one's going to be called graph B. All right, that's what happens when you change the amplitude. It was basically the parent function was the same, just added a 3 in the front and a 1/2 here, and that makes that a taller wave, and it makes this a flatter wave. On this one, just so we can clarify, let's go ahead and call this one, the first one, f of x, and let's call this second one g of x. It's just a much better way to say it. Okay, this time, let's compare. The one up above had the 3 in front of the sign. This time there's a 4, but it's not in front of the sign, it's in front of the theta. And so that actually is not going to change the amplitude at all. What it's going to do is change the period. And so let's take a look at what's going to happen. All right, on both of these, the amplitude is just going to be 1 for both of them. And so what I like to do when I'm counting by ones, like I said, give myself some space. And so here are, amplitude is up and down. I'm just counting by ones. My period, though, for my f of x function, I take 2 pi over b. And in this case, my b is 4. So that means my period is pi over 2. Whereas for g of x, my period is 2 pi. You always do 2 pi. Divide by 1/2. Well, what's 2 pi divided by 1/2? That's actually 4 pi. All right, the period is vastly different on these. And a little bit of a problem on graphing, because for my graphing, I'm supposed to take my period and take that divided by 4. And so for the period on this one, to do my x-axis, I'm supposed to divide this by 4. That means pi over 8. So I'm supposed to divide this up into pi over 8s. How many boxes do I have? 1, 2, 3, 4, 5, 6, 7, 8. Oh, good. I have 8. So what that means is this whole thing is pi. All right, this is pi over 4. This is pi over 2. This is 3 pi over 4. So I'm counting by eighths, but I skipped a space. So that's 1/8, 2/8, 3/8, 4/8, 5/8, 6/8, 7/8, 8/8. So there I have it. I want to do that same thing in the negative direction. All right, now let's think about how this is going to go. Let's start off with our f of x. The sine of 4 pi, or 4 theta, the period is pi over 8. What that means is we're still in the world of sine. Sine always starts at 0, 0 and goes up. The amplitude on both of them is 1, so I'm just going to go up to 1. And I want to go to pi over 8 and go up to 1. And then come down, and then down again, and then up. So there is one period. So that is one period. In the space of pi over 2, it went an entire period. I should go ahead and just fill out my graph. Okay, so our f of x looks like this. And back to those straight v's again instead of the curves. They really should be curved. If they're v's, try to make them a little bit more curved. Why does that matter? Well, one thing is, that's a bad line. Do you remember on our table that was like 0.7? Hang on, let's take a look. Right, 0.707 was the next spot down, and it would be the same for this graph. It would just be in a different place, but 0.707 should be my next point. So this point, halfway between there shouldn't go exactly halfway. It should be up here a little bit more at 0.7. That's why these curves are important, just to be a little bit more accurate. Okay, that is our 4 theta. Just like when it's inside, if it's minus, it means right, and if it's plus, it means left. It's like backwards of how it's supposed to be. In the same way, this 4 pi seems like it should be wider, but it's actually narrower. We've actually done a horizontal shrink. We have moved these together more, squished them together more left to right. The 1/2 is going to spread it apart more. Okay, so let's take a look at that one, because on this one, remember we calculated that the period is supposed to be 4 pi. And so our graph then is supposed to take that and divide by 4 to get our stops along the way. If I take that and divide by 4, I'm down to pi. Okay, well, what does that mean? That means that I'm going to start at 0, 0. I always do that. I always start at 0, 0, and I always go up. Because I chose this breakup of my graph. What this means is I'm going to go all the way over here to pi and go up 1. It's going to go like that. And then in the negative direction, it's going down here. I probably didn't scale my graph very well. It's okay because look, it says be sure to show the scale on both axes. You really want to do that. If you don't have a scale on there, no one has any clue what's going on because it's also repetitive. So you really have to scale it and say, how big, how tall, how wide, etc. But I maybe should have counted and had this at 2 pi over here. It would have squished these guys closer together, but at least would have given me space to have a full, or at least a half of a period. As it is now, on this positive side, I only have a fourth of a period. And on the left-hand side, I have another fourth. So really, altogether, I have a half of a wave. That's okay. I've scaled it. I've labeled it, so we're okay. But that's what's happening. The 4 pi makes them squish together more. The 1/2, 4 theta, not 4 pi, 4 theta, makes them squish together more. The 1/2 theta makes them spread apart more. So that's what that inside number is doing. The HIVO, that's the inside.